Okay, it is the moment we have all been waiting for. Best Zoom background contest. So rules are simple. To compete, you just simply have to have your webcam on. Then to become an official entrant, I want you to paste your name and your background into the chat. Okay, so something like this, Lionel Millennium Falcon cockpit. Just put that in there. That way we sort of have an official name and entrant. And then to vote, everyone else, just copy and paste the description of your vote. And then I do need a volunteer, somebody who is not participating in the contest, but is willing to be our official scorekeeper, our vote tally counter. So can I get somebody who's willing to do that for us? You yourself can't be a participant though. I mean, okay, I can do it, yes, but I don't want to.
I'll do it. I'll do it.
Yeah, okay, that's Keshav.
Yeah, I also don't have like any kind of background.
Awesome. Okay, yeah. You are the man. Thank you. Okay, so I'm gonna stop sharing. Let's put this on thing. Let's see what we've got here. Okay, so I've got a submission from Ryan. Oh, nice. Going with the meme. That's always a strong entrance. Okay, I'm seeing Felix with the DVD COVID background. That's a solid thing. Don't forget, if you're participating, throw your thing in the background. Throw it up in the chat so people can vote for it. Let's see. Oh, Spencer's got Eggert going. Man, you are not messing around. Okay, Daniel's a bit out of this world, literally. Let's see, I'm seeing Rashab getting a haircut, doing multitasking during lecture. That's awesome. Okay, remember, how you vote, you just copy and paste into the chat your favorite entrance. I can't make a poll in advance. So just literally just type in the chat which one you like. And then Keshav, you'll just tally up everybody.
All right, sounds good.
Okay, Ziyuan coming to us live from the White House press room. Awesome. Dig in that. Let's see. Akshay's got a Ben Shapiro tweet going. Okay. Michelle, is that your cat?
Oh no, it's just a cat meme.
Ah, okay. Well, still cute. And then I'm seeing, oh, Varun, is that a Kong versus Godzilla? Did you see the movie? Was it any good?
Oh yeah, really good. Yeah,
Oh,
yeah. Highly recommend.
Really good. Okay, well, I guess I got to give that a shot then.
Well, you should know what to expect from a Kong movie or from a Godzilla movie.
Fair enough. Okay, Miles, I'm seeing some Frozen action. You know, I never saw the second one. Is it good? So.
I like them all. But people think they're kind of rough on the storyline,
Okay.
which I think doesn't matter at all.
Gotcha. And then Akansha, everything is fine, right? You know, back when, I don't know if you guys were here for the fires last year. Was it last year or 2 years ago? I had the notion of like just swapping out the dog for Westwood, just putting that right in the middle. Be like, everything is fine. Just putting Royce Hall right there. Isabel, I'm seeing the cat meme. Always a classic. Okay, let's see. Are there any others? Let me see here. Scroll through here. Okay. All right. Did I miss anybody? I think I got all the entrants, right? Okay. All right. So send in your votes, folks, if you have not voted yet. Oh, we got some people in the waiting room. We got some voters. We got to admit everybody. Okay. All right, I'll give you guys another few seconds for. Oh, Vedant, I didn't see your background. What are we flat earthing it or what's going on there?
We flattened it today, yeah,
Oh,
for sure, for sure. There's only one way to look at it.
that is my second favorite conspiracy.
What's your
After
first favorite conspiracy?
Birds aren't real.
Birds aren't real? What do you think they are?
Government drones, baby.
Why, I mean, look how inefficient the
Isabel!
DMV is.
Oh, I see a kindred spirit. Isabel, can you hold that up? That's so funny. There's a whole subreddit just devoted to birds aren't real. They're all just government drones.
I'm convinced.
Wake up, people.
Reagan of all people would do government drones. I feel like there are other presidents that are more surveillance heavy, like Bush Jr. or something.
Hey man, the surveillance state knows all.
I feel like Reagan has become such a meme. And I don't even know whether that's supposed to be good or bad.
All right. Any last minute votes? Okay, Keshav, how are we looking? Do we have a winner? Okay. Drum roll, Rish. So, okay, it looks like Keshav is saying we have Rishab as our winner.
For the
Congrats,
votes.
man. So, do me a favor. Send me an email address for your little Starbucks gift card. Okay, either throw it up in the chat or shoot me an email.
Yep.
Cool. Well done. Guys, some of these are awesome. I love this. This was great. Okay. Rumor has we got to do some data science though. So sorry about that. Buzzkill. All right. Let's see. Project 1. So I kind of mentioned this last time in the chat, so I'll just kind of overview this again. This is a sort of a pretty consistent theme with this course, but one of the kind of general things that you're going to see as we go through this course is that in many ways, data science feels a lot more like an art than a precise science, in that what you will find is more often than not, it's a series of trade-offs, a series of choices that you as a data scientist have to make. There isn't necessarily a right or a wrong approach to doing it. It's just kind of understanding these choices and the consequences of doing it. And part of what our goal for this course is to do is to essentially kind of help you understand those choices and give you sort of a set of tools that you can employ when you're working on your own models. Building out those set of ingredients, building that sort of cookbook for you. Beyond that, though, again, there is a bit of kind of chance and guesswork to this. And, we talked a little bit about this last time, but like there's a reason why a site like Kaggle exists for data science, right? Where you can kind of put up contests and it's not necessarily obvious what the approach is going to be that's going to work the best. You really do have to try things out, experiment, see what's going to work, tweak things, and then maybe it'll work, maybe it won't. And as we mentioned kind of in lecture on Thursday, Project 1, the whole idea here is what I call the bake your first cake. It's the idea of you've never stepped foot in a kitchen before. We just want you to get used to the idea of like tossing the ingredients in the bowl, mixing them, turning it in the oven, putting it in, baking it, getting your cake out, right? It's not going to taste great. There's going to be a lot of things that you're not going to understand why you're doing it. But the idea is we want to get you kind of working end to end on a data science problem, with the idea then it'll hopefully give you a frame of reference that then as we work through each of those concepts, you'll then have a kind of a frame of reference to say, oh, okay, that's why I did this. That's why I did, what I did. I'm still recording. Okay, cool. So And again, specifically for project one, our general thoughts and assumptions, we assume that you've never worked data science before. We assume, we don't assume that you have any kind of pre-existing knowledge or how to do this. So the idea here is we try to give you as detailed a walkthrough, as detailed an example as possible, with the idea then that you will take the code that we've given you and really attempt to replicate it. However, in so doing, one thing I do want to kind of emphasize with this is that there really is not a one right way to do this. We do encourage you to use the coding examples that we've given you, but if you happen to have done this before, if you know of some alternative libraries, some alternative ways of implementing these things, like that's perfectly fine. You will not get it wrong if you don't use a particularly Python method or a particular thing. As long as we ask for a certain output and you generate it, great. The other thing is, particularly for this exercise and probably for project 2 as well, you will not be graded on your model performance. Again, we just kind of want to see you go through the steps of this. We really are not going to be looking at the performance of it. Probably not until project 3 will that be relevant. So I do kind of want to call that out. So what are the specifics that you're going to be asked to do? So the first thing is get acquainted with the data that you have. And by the way, I'm kind of curious in the class, are you all data people or are you data people? I haven't had a poll made. I don't know if I want to do it, but I'm kind of curious. And the funny thing is, after I put that meme up, I became super like self-conscious about it. It's like data. So I don't know if anyone has like really strong opinions on data versus data, but yeah. I don't think I'll waste time polling you guys on that, although I did prep a poll specifically for that. But so I will say, so generally, here's what we're going to be asking you to do. And we'll kind of walk through the code so you can see a little bit about this. But the first and most obvious thing is loading your data set. So you're reading in your CSV file, whatever your data set is, and then kind of getting a feel for the data that you're going to be working with. So displaying the first few rows, understanding that the types of data that you're dealing with, understanding, visualizing it, running a little bit of statistical information. Again, all the idea of saying, okay, as a data scientist, what is the sandbox that I'm playing with here? What are the potential features I have to work with? What are some things I need to be aware of? What are the problem children in my little feature set? What are the good ones? What can I kind of do with this? So that's kind of the first step. It's that exploratory step. What am I working with? Once I kind of have seen that, the next step is just data prep. And now this is where you kind of, as a data engineer, begin to kind of work with your data to turn it from something that is raw and not necessarily something that's particularly useful into ultimately something that can be fed into a learning model and is of value. You're maximizing the amount of useful information that you're feeding into your data. And there's a whole, we are going to spend a fair bit of time just walking through what that looks like. By the way, I have no idea what, this meme has nothing to do with the slide. I just thought it was hilarious. I feel like I'm regressing in terms of my humor. It's bad. Like when I started these slides, I made the effort to like make the memes topical, and now it's just like, whatever. Bagels. So you will be doing things like, as just an example, dropping columns for your data. So there's going to be features that you're just going to say, you know what, this is just not relevant for me. I'm not going to do anything with these. I'm just dropping them. There's also a lot of exercises around augmenting your data. So oftentimes there's very interesting kind of latent patterns or sort of elements in your data that you may want to kind of make explicit, that you want to feed into the model that aren't necessarily there. And so we're going to spend a lot of time thinking about that and what possible strategies you may have for augmenting it. There's also, and we're also spending a bit of time talking about data imputation. So, when you have null values in your data set, how do you deal with that? Because that's a non-trivial question as a data scientist to deal with and to kind of figure that out. Then once you've kind of done that, you sort of then need to divide your data set cohorts into training and testing cohorts. Has Professor touched on the whole train test kind of division and why we do what we do? Nope. Okay. We're gonna spend some time on that during this discussion, but I'm gonna give you the 10 seconds on it now with the idea that we're gonna kind of circle back to that right at the end. But it's the whole idea that, so at a very high level, the process of machine learning is a form of reinforcement learning. If you've seen it, it's the idea that you input your data into this model. The model will generate a prediction, and then based on how it does, there's kind of an updating rule. And depending on, and we're going to keep this at a very high level because each learning model works a little bit differently, how it does that, what it tries to optimize for, things like that. But the general idea is it's this kind of form of reinforcement learning where you sort of feed it in that data, it generates a prediction, it tests that prediction against what the actual thing is supposed to be, and then based on that result, it adjusts itself. And it's the idea that the learning part is it continues to iterate and iterate and iterate until it sort of converges on an optimal solution, the thing that gets it right as much as possible. And again, I'm going to leave that super high level now because we're going to spend weeks on what that means and how that works. But just at a very high level, that's kind of where it's getting towards. But then, and this is kind of the other thing that's kind of interesting, and this is the Zen of machine learning data science. There is this balance that you as a data scientist want to hit, where you want a model that kind of works well, but you also don't want a model that is overfit to your particular data. And what I mean by that is that this is kind of the underlying challenge. This is sort of the core challenge of a machine learning approach. And it's the core challenge of statistics, really, which is the idea that when you are doing a machine learning problem, you are trying to infer rules about sort of the broader universe based on just a subset of data, right? You have your data set is a snapshot of the universe, and you want to use that snapshot to try and kind of make this sort of universal grand set of rules for how the real world works. And invariably, your data will not necessarily be perfectly representative of that universe of data. You know, there will be skew, there will be bias, there will be things about your data that are maybe not fully representative in the universe of data. And so you can very easily get the scenario in which you can kind of train a model against your particular data set that works perfectly. Like it gets it right every time. But the problem is it doesn't generalize well, because all you've done is you've trained it against your little training set, but you don't have, but it captures all of the nuances of and quirks of your particular data set, but it's not reflective in the broader universe. So how do we control for that? How do we kind of make sure that the model we're training is not just picking up all the random static and noise and things in our data? To do that, we then have this testing cohort. So that's why we kind of pull some of our data out, we hold it aside, we don't train our model against it. And then once we have our model, we then take that model, we plug it in against that test data, and we say, well, how well does it perform against this? And the idea there is to answer the question, how well is our model likely to generalize in that universe of data? When we expose it to data we haven't trained it against, does it still perform well? Or have we maybe overfit and suddenly when we expose it to new data, it just falls apart because all it was doing was just kind of reiterating the thing. So it's that kind of, it's a way of thinking of it like a sanity check. So we're going to do that. And again, we're going to talk about that a little bit more later. And then probably, and this is going to be the thing we're going to probably spend a fair bit of time on today, because this is probably the hardest part of the code, is pipelining your data. And the whole notion here, and again, we're going to get into this. This is just the overview. So I'm just kind of throwing you the 30,000 foot view, and then we're going to get into the weeds really quickly. But the idea here being that there is much like when you're doing software development, right? You're going to be testing out certain codes, you're going to be doing things, but then there's a point at which you move your code into production. And with data science, it's the same thing too, right? A lot of times you're building a model for spec, you're building a model to sort of feed into a business process, feed into kind of a software stack. And you need to kind of take what was sort of an experimental approach and package it up to sort of a nice, beautiful, concise series of methods that you can kind of call on your data and sort of have it in a production environment. And that's really what pipelining is. So then once you've kind of done all that, you're actually going to train your learning model. And in this case, for project 1, we're going to do a basic linear regression. So we mentioned this last time. There were at a very high level, there's 2 types of machine learning exercises that we'll generally do. Do you guys remember, like, at a very broad scope, like what those are? All right, I'm going to kick it over to you. The 2 very simply are, the first is sort of a prediction model. So the output, your y variable of this, if you think about all your inputs, all your features as x variables and your output being your y. So for this one, your y is a discrete number. So it can be a value. So in this case, for instance, like we're trying to build a model to predict Airbnb listing rates. So the y there is the dollar amount for the rate. So here you're going to do something like a linear regression. And there are a few different models that you can use for doing that, but linear regression is by far the most popular. And you have this, you basically are trying to train this trend line. And this trend line here will sort of allow you that when you're given, let's say, a point here on your trend line, you can kind of say, oh, okay, I'm going to estimate the y value to be this. And that's what my model is going to give. So we're going to, as part of this exercise, we're going to train it. We're going to then test it, and we're going to measure those results. And for this one in particular, we are going to use something called mean square error. And again, we're going to spend, that's another kind of very interesting topic that you can get surprisingly in the weeds on, is like, what does success look like? And we're going to get into that. But like, because with both classification, oh, sorry. The second thing I should mention, so our first thing was that prediction. The second thing is a classification exercise, where instead of y being a discrete number, y is a classification. So if it's a binary classification, it's like a 0 or 1. You could have a multi-class classifier, but it's the kind of thing of predict sick, healthy, cat, dog, good student versus bad student, right? Things like that. You have, in that case, it's a classifier. We have a discrete number of classes, and then it's your job to predict sort of one of those classes. So how we measure success, how we measure what a good outcome looks like, can vary pretty dramatically. And there's a lot of kind of strategic choices for why you might choose one measure of success versus another. So in this case, for this exercise, we're going to use one of them. We're going to use something called mean square error. And I'm going to take a little bit of a detour and just kind of run that through with you. Essentially, so mean square error is the idea that you take the difference between your actual versus your predicted. So if your blue line here, that's your trend line. And then your sort of pink dot here is your actual. The error in this case is that red line, right? It's the difference between that two. And then you just kind of, you take the sum of those. So you sum up across all the error terms for your entire data set. And then you square it and then take the average over your total number. Now, quick kind of pause here, quick kind of thing here. Why do we square our term here? What's the reason do you think that we might want to square our values?
Get rid of negatives.
Yeah, perfect. So exactly right. We want to get rid of our negative terms because, right, you can see here we have some positive error terms where we've under predicted, and we have some negative error terms where we've under predicted, or the opposite. But the whole idea that then if we sum this up, we may actually get a number that's close to 0, even though our actual error is pretty large, but just because the signage is different. So we need to control for that. So that's on one hand why we square it. But, and this is kind of an interesting thing of like why you do different things. There are different ways we can control for that. So squaring it's one of those. Another one is we just take the absolute value. So, and that's I think that's another metric called MAE, mean average error or absolute error, where we just sum up and take the average of the absolute value of that error. So another kind of reason in this case why we take the square of something, and this goes back to like how you value certain things and how your model looks like, is that when you square your terms, you are disproportionately penalizing higher magnitude errors. Right? I mean, if you think about it, like if you square, 3 squared is 9, 4 squared 16, 5 squared 25. Right? So like even just slightly higher magnitude errors can get penalized much heavier. And that goes to the type of model and the type of errors you want to make. So a model that uses, for instance, MSC might say, you know what, we're okay with a lot of low level errors. Like these we're okay with. As long as you're close, that's fine. But we just don't want to be making huge errors. We don't want things like this happening. So we're going to disproportionately penalize large errors that occur in your data set. But as long as it's sort of a small error, we're not okay with that. Something like MAE takes a more balanced approach and says, you know what, we just want the overall error minimized, but we're not going to sort of bias any particular thing. So what's right, what's wrong? Again, it depends on the specifics of your particular project and how you want to prioritize certain types of errors in your model. So I did just kind of want to flag that as something just to kind of think about as you're working through this, as like one of just the cohort of options that you as a data scientist will have. Then just like homework 0, you are going to output your things as PDFs and submit the PDF for us. So, we want to see your code blocks and we want to see the outputs. Does anyone have any questions about that? I mean, I'm kind of hoping not, just because you sort of went through that with homework 0, but like any questions?
I mean, for the first project 0, I just took screenshots and then put those into a PDF. But I know someone said there's a way like to install something and then export it, the whole thing as PDF, but I wasn't going to do that.
Okay, I will show you guys that right now, in fact. So if you look at this, so definitely, because this one is just much bigger, you could theoretically try to do screenshots, but that's just going to be onerous. But yeah, if you have LaTeX running locally on your device, you'll have the ability within Jupyter, you can do a download as, and then PDF via LaTeX. And then it'll hang for a moment while it's generating. But let's see. Okay, so then it populates and look at that. We get our beautiful LaTeX notebook with inputs and outputs. But yeah, that's generally the way I'd recommend. There are other ways to do it too. So, if that proves problematic, there are alternative approaches, but that's what I've found to be the easiest way to do it. And I think the only requirement is you just have LaTeX running locally. So yeah, you can also do it via Colab. And again, if you're comfortable working with Colab, perfectly fine to do that with that. So definitely feel free to use Colab. You should be able to export as a PDF from Colab as well. I know students in previous quarters have done that and it's worked well.
So just to clarify, it's okay if we include not the exercise parts in the PDF.
Yeah, absolutely. Yeah.
All right.
In fact, we're kind of, that's what we're expecting. Like, we don't expect you to go through and manually prune all the non, I mean, that's just onerous. Yeah. No, whatever, like just submit the entire, literally just submit this, like all the stuff up front included. Yeah, definitely don't feel the need to like cut all that stuff out of your notebook. But yeah, I'm glad you clarified that.
I have another question about submitting. You mentioned exporting to LaTeX, but what's the advantage of doing that and then exporting from LaTeX to PDF versus exporting to PDF directly from Jupyter Lab?
So if you're able to, so at least for the Jupyter that I have, it uses LaTeX to generate the PDF. If you have an alternative way of generating the PDF, so this does a PDF via LaTeX, so it uses that to generate it. If you have an alternative way of doing that, again, power to you. There's no necessary reason to. Oh, are you guys able to see my screen? It says sharing is paused.
Oh, we see your slides.
Oh, crap. So like the whole time I was talking, you didn't see that? Okay, hang on. Sorry, new share. Oh, okay, sorry about that. Okay, now can you see my screen?
Yeah, yeah.
Okay, so then, sorry, let me go back here then. So what I was showing before was in your notebook, you have the ability here, it'll say download, and it gives you the option PDF via LaTeX. So that was the thing that I was showing, and then it just generates it and then prints out to something that'll look like this. And I was saying this is probably just the easiest to submit. But again, if you have an alternative way that works and it's legible, then by all means, I don't think there's no. You won't get docked points because you didn't use a particular framework for generating your PDF.
Cool, thank you.
Yeah, absolutely. Okay, all right. So yeah, any questions about submission?
Apparently for homework 0, they what RPass wrote is you only submit the code you wrote and its immediate output.
Mhm.
So he said to copy over the necessary text to an editor.
Mhm.
So, and I'm seeing this and it seems a bit more complicated.
Yeah, so I think that the thing to emphasize here is whatever works best for you. So as long as we can see your inputs and outputs, we can work with that. The graders can work with that.
But you don't need to run the code, right? Like, would you prefer it in a... I'm assuming you're going to be running the code just to make sure it's valid.
No, so we are not. So that's the thing. We are not going to run the code locally. That's why the only thing that you're going to submit is a PDF. So we're not going to run the notebook. We're not going to ask you to submit your Jupyter notebook. That's why we just need to see inputs and outputs of it.
You're okay. Yes.
Yeah.
Thank you.
Yeah, no, absolutely. Great question. But yeah, so whatever works best for you all, whatever you find is easiest to do, by all means. And if you have any questions about a submission, if you're like, here's how I generated like this look okay, you can always just send it to me in advance. And I can kind of give you a thumbs up or down. But in general, I'd say the only thing that we've had sometimes just to be aware of is sometimes the PDF that gets generated isn't legible for whatever reason. So that's the only time we've kind of sent them back and be like, we can't really make out what's happening here. But again, as long as we can see your code and as long as we can see what it generates, then we're good to go. So, okay, so that at a high level view is what you're going to be asked to do for project 1. So if there are no other questions on that, let's dive into some of the code. Okay, so here's some specific stuff I want to talk through with you. These are things that you're going to be asked to do as part of the project and just kind of understanding both, I guess, sort of the underlying theory behind it and then just kind of how that works. First up, we're going to talk about augmenting data. So again, that's kind of engineering new features in your data. Imputing data, again, that's sort of handling the nulls. We're going to talk about how you also kind of handle each of your data types. And we're going to focus on 2 things. We're going to focus on categorical data and we're going to focus on numeric data. We're going to spend a lot of time talking about pipelining. We're going to talk a bit more about splitting your data and then interpreting the results. So that is what is up. Okay, augmenting data. So the first thing to note is that we can augment both rows and columns. So, and when I talk about kind of augmentations, it can really be two kind of things. So when I augment rows, what we're essentially saying is we're sort of creating new data. If you think about like each row in your data set as like a discrete kind of data point, when you augment rows, you're sort of supplementing your data. You're adding new data that wasn't necessarily in your data set previously. And a very common approach for this, if you look at like computer vision data sets, are taking images and then kind of doing transformations to it. So if like your original was a 3, doing like various things like flipping, padding, cropping, rotating, but and kind of doing these standard transformations and then adding those to your data set. Another great example of this is time series. If you are sampling at discrete intervals, well, you may want to kind of want to infer intermediary points, look at like trend lines and then insert sort of additional rows of data as those in between things. But then there's augmenting columns, and there's and this is the idea that there are sort of patterns or again, data that's sort of latent within your data set that isn't necessarily immediately obvious or transparent in the data the way it is right now. And the first example of this is something like a log transform. So something that isn't necessarily immediately linearly interpretable, and this is kind of a great example of this so this is, I pulled this off a paper, but this is like a scatter plot of brain weight as a function of body weight in terms of both raw data and log transform data. So as you can see here, we're looking at sort of the relationship between brain and body weight. And here, we're not really seeing something that looks like much of a trend, but when we do a logarithmic transformation of the data, suddenly we're seeing something that looks like a much nicer linear kind of trend line and relationship. Like there's a very strong correlation here between these two variables. So again, not something that was necessarily obvious in the data in a raw form, but once it goes to the transformation, suddenly you have a feature that's probably really, really useful if you're trying to get a predictive thing for the other. If you're trying to predict your brain weight using your body weight, suddenly you have a feature that's probably going to be very powerful for that. Another kind of great example of this is time blocking. So, and this is something that we deal with a lot, particularly if you're dealing with like time series data, where you may have kind of a feature and a label mismatch. So let me give you a great example of this. Let's say you are collecting data on a test subject on like a continuous basis, or let's say you're collecting it like hourly, but your label, let's say you're labeling their overall health on a given day. That's done on every 24 hours. Maybe you send them a survey and they fill that out. So your labels are coming in every 24 hours, but you're getting data hourly or every minute or whatever. But so there's that mismatch. So one thing to kind of address that mismatch is you may try to kind of aggregate some of that up. So sort of aggregate up like at 24-hour intervals. So you may take like things like basic, things like min, max, average type deals and say, okay, for this 24-hour interval, let me do a raw count. Let me do a max value, a min value, an average value, things like that, and return that as a feature that I then plug in against that label. So then there's that direct match between label and feature. So that's an example of something you might do. And then there's categorical transformations. We'll probably spend a little bit more time on that, but I do kind of want to just kind of mention that. But oftentimes you may have values that are continuous. And the example I give here is latitude and longitude, but may actually be more useful when blocked into kind of discrete things. So converting latitude and longitude into discrete neighborhoods or something like that. And so, again, these are all examples of things that aren't necessarily kind of direct linear things that are already implicit in your data, but could be very valuable from a data engineering perspective. Now, for project 1, you're not going to be asked to do anything on this level. You're asked to do very basic features. I mean, literally like multiply 2 features together, divide 2 features together. So not data augmentation that's actually going to be particularly useful for this exercise. It's really just about you going through the exercise of doing that. So I do kind of want to mention that explicitly. You're not going to be asked to do anything too complex with that. And so let me actually pull up, we'll just kind of run through this while we're doing this. So, okay, so this is, by the way, this is the project one. I don't know if you've seen this yet. If you've downloaded, if you haven't, please do so as sooner than later. But just to kind of walk you through at a high level what we're doing. So if you recall last week, we sort of started with pandas and just like a great library to work with data frames. So in this case, we're loading our data set. We're kind of looking at it. So we're looking at, this is California housing data. So we're looking at latitude and longitude values. And then we have features like housing, the median age for housing, the total number of rooms, total bedrooms, population, household, median income, median housing value, ocean proximity. And I guess the interesting thing here to note is that essentially we're looking at whatever kind of, so there are discrete points here. And it looks like it's every, I guess, 10th of a, or 100th of a decimal point on the latitude longitude thing. So whatever geographically that corresponds to, there's sort of a summary of data for that. So we have the average age of the house. We have the total number of rooms for all houses in that, the total number of bedrooms, the total population within that kind of geographic segment. So we can kind of look at that. The next thing we have us do here is we pull the info method, which you'll remember from last time. And that kind of gives us a nice view of our data types. So we're looking here and we pretty much have everything is already in float form, which is great. Because if you recall, one of the biggest problems we have a lot of times is our data isn't already in a numeric form. And so in this case, it looks like everything is there except for ocean proximity. Ocean proximity, looking up here, okay, it's this, it looks like it's a categorical variable. More on that in a moment. But we sort of have these values like near a bay, whatever. Okay, so we may have to do something with that. Aha. So indeed, let's look specifically at that. And we have those values there. We also kind of call out, and again, you saw a lot of these functions in the pandas lab that we did last week, but just to sort of note, you can kind of pull individual rows, you can pull individual columns as we've seen. You can kind of look at, this is sort of another interesting thing if you want to just see just how it breaks down. So there's this really useful method called value counts that you can call for ocean proximity. So we can see here, it looks like there are, so there are 5 discrete values for it. Less than an hour from the ocean, inland, near ocean, near bay, island. And we can see here the number of rows that we have associated with each one of those. The other thing, and we kind of mentioned this last time, was the describe function, which for all of our numeric features, so everything that's already in either int or float method, we can get some nice basic statistics. And so we can get kind of a raw count of the number of features we have. We can get their mean, standard deviation, min, percentile, and max values. So just sort of a nice little output there. We then walk through visualizing the data set. This is something we hadn't gone through previously, but again, pretty easy to kind of just see here where, so in this case, so there is the library matplotlib, or lib, matplotlib, that you are going to import. And that will basically give you all the functionalities to do these visualizations and graphs. So very easy. In this case, we kind of want to look at like histograms. So we want to look at like a distribution of values based on sort of the number of instances. So this kind of gives us a nice feeling for like what our different features are, how they look, things like that. So
if we're not only going to be turning in the outputs from these cells, is it necessary to use like the save figure command, or can we just use show and then just copy that into our PDF?
Sorry, what was the question again? Sorry.
So if you scroll up in where like all the matplotlib is imported, there's like a function to save the figure.
Yeah, that was just, I'm sorry. Yeah, you don't actually need to use that. Correct. Yeah.
Okay, thanks.
That's code that he included as like, oh, this is kind of a cool thing you could do. Yeah, that exports your figure as a image, but you don't need to do that. But yeah, thank you for flagging that. Mm. Okay, so this was something that we had also kind of mentioned, how you may want to take discrete, a continuous variable and turn it into a categorical one. So in this case, if you look at medium income, so it is a continuously valued thing, that shifts over time, but we may want to turn that into something that's a set of discrete categories. You may want to go like low, medium, high income things. So this is just some sort of, this is a nice kind of example code that you can do. Again, a really great just function that's built into Pandas that allows you to kind of essentially bin your data and divide it into these discrete bins. And that can also be very useful for a number of reasons. You can also kind of do a scatter plot where you can sort of plot your things against longitude and latitude. I will say that we do ask you to kind of replicate this for the New York Airbnb data, but please do not feel like you need to reach this level of impressiveness, particularly given the time frame that you have. You turn in something that looks like this, you'll get full credit. I don't want you guys like losing sleep over this. If you can hit this, this is great. Like it's a nice kind of aspirational thing to get to. I mean, from a data visualization standpoint, it's beautiful, but please do not think that this is the level that you have to reach for the assignment. Turning in something like this or even this is fine. So I do want to note that. Okay. Correlation matrix just kind of looks at the relationship between variables. So yeah, so Seaborn. Okay, so there's a question about Seaborn. We do use, I think we use it at least once in project 2. But again, if you're comfortable, if you know Seaborn and you're comfortable and you can generate the outputs we ask you to do, like that's fine. Like I said up front, this is just sample code for you to use. It's not, you have to use this. So definitely, don't feel like compelled to do so. If that's not true. Okay, so augmenting features. So this is the whole thing, just was to get to this point here, augmenting features. So here's some examples that he gives here. So in this case, we're going to manufacture a few new features. So remember, our data set, looking at it, we took each sort of geographic point, each little dot here, and we notice that a lot of those are aggregations. So it gives us total population, it gives us total number of rooms, it gives us total things, but it doesn't necessarily give us a per capita understanding of the housing stock there. So one of the things we may want to do is we might want to look at a more like per capita basis. So let's manufacture a few new features. So the first one being rooms per household, right? That makes sense. Given the total number of rooms, that doesn't really tell us how big these houses tend to be, how opulent they tend to be. Rooms per household, that'll tell us that. Again, bedrooms per room, that's another kind of indication, right? What's the ratio of bedrooms to rooms? Obviously, smaller houses will have more bedrooms relative to rooms. Larger houses will tend to have more non-bedroom rooms. And then of course, population per household, right? That's sort of obviously another thing. The more people per house will also kind of give you a sense on the relative size and density of those things. And so it's very easy to create these new features in Pandas. You can literally, you just define, much like you would for like a variable, you can define a new feature. So in this case, so rooms per household, I'm just defining a new feature in my housing data frame, and then just set it equal to a mathematical relationship between those. So in this case, to get rooms per household, I just take my current total rooms, divide it by the number of households, and look at that. It'll give me rooms per household. So yeah, Pandas just makes it just super easy to do things like that. It's just, and then, you can just output that and you can kind of see some of the things associated with that. Okay, then we're going to get to data imputation. So let me pop back to my slides. But yeah, so that's data augmentation in a nutshell. And then let me just say for project 1, you're going to be asked to augment a few features. Don't put too much thought process into that. It's okay just to do random kind of things here. We're not expecting anything. Again, we want you to go through the exercise of doing this, but don't fret about whether or not a particular feature makes sense or not. We really just want to see you go through the exercise. So if it works, it works. Okay, for the Airbnb data, are you using all attributes for scatter matrix? Oh, that's a good question. I think use all the features that we tell you not to drop. So we do ask you to drop a handful of them. Here, we ask you to drop name, host ID, host name, and last review. So, but yeah, for the rest, we do want to see the rest of them. So thank you for asking that. Jakin. Yeah. Okay, so that's data augmentation. You guys feeling okay about that? All right, back to the slides we go. So data imputation. So we've been kind of hinting at this, something we need to resolve here. Let's talk about sort of a null value here, and let's kind of specify, because I think null often gets confused for 0, and it's not a 0, right? So here's, I think a toilet paper is a great example here. Null is when you have a feature defined, but you just simply have failed to input a value for it. So it's not a 0 and it's not undefined. It's there, it's defined. It's just there's no value associated with this. And there are multiple strategies that we can take for this. Do I have a slide with this? Okay, no. There are multiple strategies we can take for dealing with this. Let me sort of pause here and kind of throw that to you guys. What do you think? What might be some approaches you might take to dealing with a null value?
Can I just remove them?
Remove them. Okay, so yes, you can, but let's be more precise. What would you be removing? Specifically, are you going to remove the column or the row? Both, neither?
I'd probably remove the row.
Okay, perfect. Yeah, so that is a very valid approach. That might say, you know what, if I have a particular data point that is missing values, I might want to remove that. Let me ask you guys, what might be an advantage or a disadvantage to doing that?
What if you have multiple columns, but that row is only null in one column?
Okay,
Then,
good. So
yeah, I would just say you could like omit it from a graph that uses that particular column.
Yeah, so
and keep
okay.
it for others.
So Axel, I think it's a good point. It becomes so the reason this becomes valid is not just for the visualization. I mean that is important, but it's when you actually plug it into your model itself. So, you know, for instance, if you're doing like a linear regression, it's just a basic example, right? You're training the coefficients for each of those features. So, so it becomes a little bit tricky in that case, how you would kind of exclude certain kind of rows or elements from that and not others. So again, not to say that you might not be able to work something out around that, but just to say that does become tricky, and it's different. It's a different exercise than visualizing it. But yeah, so one example that is just say, you know what, any row that has missing data, just consider it incomplete and drop it. And that might be a very valid strategy if you have, for instance, a huge data set. If you have more data than you could possibly use or want, then you might say, you know what, I'm just not going to deal with anything that's incomplete. I'll just drop it. I have so much data as is. I don't need to worry about that. Another reason to drop a row is if you're dealing with multiple null values. Like if you have, you know, it's very different if there's like a 1 null value in it versus like if half the data is missing. At that point, you might say, you know what, this is junk data at this point. This is just not worth holding on to. Another approach we can take, the inverse of that, is dropping the feature itself. Is saying, and again, kind of same logic, right? If you're missing a handful of values from it, then you might say, you know what, it's worth holding on to, particularly if I feel like it's a really useful feature. I want to hold on to it. But if maybe like over half of your data set is missing that feature, then you might say, you know what, probably not worth holding on to this. This is just not, It's just not giving me enough useful information. So let me just drop it. What else could we do? What else? What might be some other approaches that we could take specifically to dealing with null values? Is there anything like statistically that we could do maybe to maybe kind of infer a number or put in a number there, maybe arbitrarily? So, okay, I'll just mention a few of these. One obvious example is you could just set an arbitrary value. For instance, like a 0. Just say, okay, well, if it's a null, just replace null with 0. And there's an argument why you may or may not want to do that, but you could do that. Another thing you could do is take the average. Particularly if you have a data set that's normally distributed and it's like a nice thing, you might say, well, insert the median value or insert the mean value. So whenever there's a null, just insert mean. That's something you could do. There's also some really cool things that can say like, you know what, let me look and see if some features are correlated. And let's say, you know, that going back and like visualizing your data, if two features in your data set are very closely correlated and you happen to have that, you happen to have a value for one of those features, but not the other, maybe I can use that correlation to infer the value for the other one. That's another kind of cool strategy that you can take for like imputing your missing values. So a lot of really cool things you can do. This is a homework question. So, you know, basically that's something to sort of keep in mind. And I'm going to show you the code for that. There's a really kind of nice code, but we're going to get to that in a moment. But I do kind of want to first talk about categoricals. So this is going to be something that you are going to have to tackle as a data scientist. And that's the idea that you're going to be presented with data that is useful, that you will want to include in your model, but is not in the form that you can easily use. And so I put in a sample exercise code with this. But let's say we have a data set here and we have a set of various institutions around UCLA. We have neighborhoods associated with them. You have the type of drink they serve, and then you have the average price associated with it. And so let's say you want to build a predictive model for price. Okay, so let's look at the data that we have here. So, and this is, if you're looking here, this is our week 2 sample code. So if you pull that up, so we read in our data set. And by the way, for this one, we did like a complicated thing where he actually defined a method for reading in your thing and then like called that method to actually load the data. You really don't need to do that. There's already a native function read CSV. So you could just do that. It's just a lot easier. So you read in your data. Let's just visualize it. Okay, so, and then let's look at what we've got here. So here we have our price, which is in integers. Okay, that's great. And then we have name, neighborhood, and type. So those are all in the form of objects. So none of those we could theoretically insert into our model as is. And we know we probably need to use them because that's the only data we're given. Now, of these, name is probably not going to be a useful feature for us. I mean, these are all unique values. It's probably, I mean, maybe you could do some kind of semantic analysis and maybe kind of figure out something and it would refer to, maybe. But I mean, a lot of work to get there. So easier, let's just say, let's just drop that. So we're going to do that. So our data, we just do, again, native pandas, expression, drop, name, boom. So now our data frame is down to neighborhood, type, and price. So now neighborhood and type, like we realize these are probably going to be useful things for us, right? Because the neighborhood it's in, will that correlate to price? Sure, right? A more upscale neighborhood, you would expect to pay a premium for your things. And then type, will that sort of tie to it? Absolutely. Alcohol, as you would expect, would be a very different price point than boba. All right, cool. So, we know those are useful, but how on earth is that going to be interpreted by, let's say, a linear regression? So we need to, as a first step, we need to convert these into numeric features. And so that's the first thing that I'm going to kind of introduce. First thing, very easy thing we can do is something called a label encoder. And that is just kind of a nice, easy thing that you can do that will take any feature and convert all the discrete values of it into sort of numbers associated with this. So you can see, in this case, we import label encoder. We then take that feature. We then run the label encoder on that feature, and then we output it. And then look, suddenly what had been neighborhood, so now is transformed. So Westwood, it seems like, has been assigned 2. Santa Monica has been assigned 1. Brentwood's been assigned 0. And alcohol's been assigned 0. Boba's been assigned 1. So now, good news, this data is now data that we can plug into a linear regression model. Right now, this is something that our machine learning model can work with. Are we done? Are we good? Is this, what do you guys think? Is this, can we kind of go home? Are we good to go? Or might there be a problem with this approach? Now I'll give you a hint. It is on the slide. Okay, I will, I guess, just jump in there. Then this is potentially problematic because the numbers that we are assigning are arbitrary, but the associated relationships aren't necessarily. In that, by assigning 0 to, let's say, alcohol and 1 to boba, you are assigning a certain ordinality to your data. You are assigning a pattern to your data that doesn't necessarily exist. And specifically, let's look at neighborhoods. So we've made Westwood 2, Santa Monica 1, Brentwood 0. We have said that there is a relationship there, that Westwood is greater than Brentwood. And we've also made a relationship that says Westwood is closer to Santa Monica because a 2 to 1 versus a 2 to 0 you're in Brentwood. So we have implied a ordering, and we have implied a relationship that isn't necessarily true. And the easy way to think about this is thinking about like this data compared to age. So if I have a feature of age, let's say years that the bar has been open, for instance, 19, 20, and 2. Those aren't arbitrary, right? There's a relationship between those. 20 is clearly greater than 2. And not only is it clearly greater than 2, but 19 and 20 are clearly closer together and should be treated as being closer together than 2 is. And if I just swap those numbers, if I make those numbers random, I'm losing that information. So clearly that's problematic because we know that we need to sort of convert our categories into numbers, but by doing it in numbers, we're implying relationships and we're implying an ordering and a hierarchy that isn't necessarily the case. So how do we handle that? One hot encoding. Oh, my slide is not done nicely. Okay, hang on, let me actually fix that. There we go. Okay, now I can actually read what I wrote. Okay, so it's this really cool idea that says instead of kind of assigning numbers at random, let's take each discrete value of a feature and let's create a binary feature in its own right. So for instance, for neighborhood, rather than treating it as one column, let's take each neighborhood. Let's take Westwood, Brentwood, Santa Monica, and let's make each of them a feature in its own right. And let's assign a binary present or absent value to that. And so that's exactly what you're going to see here. So in this code, we're instead taking a one hot encoder. We are taking our values here, and then we're sort of applying that. And so we're taking, so what had been a single dimensional feature neighborhood is now a 3-dimensional array, where this first feature here appears to be Brentwood. So you can see present, absent. This second feature here is Santa Monica, present, absent. third feature here is Westwood, present, absent. And again, the advantage of doing this is something you can put into a learning model now. Our linear regression model, just an example, can now create coefficients for each of these, can say, okay, well, here's a coefficient associated with an establishment being in Westwood. Here's a coefficient with an establishment being in Santa Monica. Here's one with them being in Brentwood. So we have something that's usable. We have something that we can our model can learn from, but it's not something that assigns a relative weight or value to it. So that's kind of the cool idea of one-hot encoding. Do I have another slide on this? Okay, no. So let me pause there. Do you have any questions on one-hot encoding?
Like for each possible feature, we need like an extra bit for it. So like if we had 4 possible neighborhoods, then we need 4 of them.
Yeah. Okay, Godfrey, great question. So yes. So and I think you're touching on something that's actually going to be kind of a key decision factor for one-hot encoding, because this is going to be another homework question, is whether or not you actually it makes sense to one-hot encode. And one of the things that you're touching on is essentially that every discrete value in your categorical gets its own feature. So in this case, we have 3 neighborhoods. So each one gets its own feature. Now, if I had a category, let's say state, for for US state, well, there we have 50 states. Theoretically, you would have 50 features as a result. So yes, and that is not necessarily a good thing. And this is something that we're going to get into in depth later on, but just something for you to be aware, something that is going to be a factor in the homework is going to be you as a data science do care about the dimensionality of your data. Because, and again, we will get into kind of the mechanics of why this is, but generally speaking, you do not want your data to be, to have sort of an overly high dimensionality. The more features you plug into your data frame, generally speaking, the more likely it is that you're going to overfit your data, and the more likely it is that your model is going to underperform. And so this is one of kind of the big trade-offs oftentimes that data scientists have to make when it comes to including or not including these categoricals, is going to be if you're going to explode the dimensionality of your data set. So again, using the example of states, if you're going to explode the dimensionality of your data set by creating 50 discrete features, that's not good. And so generally speaking, you might look at that and say, you know what, probably not worth one-hot encoding in that case. Maybe in that case, an approach may be either just to drop it outright, or if I do want to include it, maybe I have to concatenate my data frame. Maybe I'll do it regionally, where, instead of 50 states, I'll do a West Coast, Midwest, Northeast, Southeast type deal, right? Maybe I'll do sort of discrete categories and then run that there where I only have like 5 or 6. So that might be something I'll have to do. So that's one reason why you wouldn't necessarily want to one-hot encode your data. What's another reason potentially why you wouldn't want to one-hot encode a numeric feature? What do you guys think? Okay, let me throw another one at you. So I mentioned earlier that part of the problem with label encoding is that there's that once you assign these numbers, it implies a relationship and implies a hierarchy. And in this case, that was wrong because we didn't want to imply that. We didn't want to imply proximity and hierarchy to neighborhoods. But there are times when we do want to imply proximity and hierarchy. So classic example of this. Let's say I have a category. In fact, it's something we deal with. Let's look here. So we have, so Sajjad created, remember, he took income category and he took what was a continuous variable and he created a categorical variable where he created 5 income categories, 1, 2, 3, 4, 5. And here, by definition, these are a hierarchical relationship, right? 1 in this case being the lowest quintile of income, 5 being the highest. So in this case, there is a relationship and it matters. Something being in a 5, something being a 5, it tells the model that 5 is greater than 1. And that's important, right? That's relevant data. We want to include that data. If we one-hot encode that, if we take these 5 values and we create a feature for 1, a feature for 2, a feature for 3, a feature for 4, a feature for 5, we've essentially broken up that information. And we're in effect feeding less information into our model than we otherwise would have. So that's not great. We don't want to be doing that, right? Because in a sense there, you're taking an existing relationship, you're taking a meaningful relationship, and you're breaking it up. So whenever you have a feature, and again, income is, I think, a great example of this. Age group might be another one, right? Youth, adolescent, young adult, middle-aged, elderly, right? There, again, there's sort of a natural ordering, a natural hierarchy. If you have a 0 to 4, 0 to 5 associated with that, you don't want to break that up. You want to maintain that relationship. So that's also a homework question to be aware of. So any questions on that? But again, that's kind of just at a high level. This is the sort of thing you as a data engineer have to kind of figure out. And there isn't always a right answer to this, because you will see a lot of features like this where you're like, is this useful information? Is this not? How do I handle it? What's the right way to handle it? And there isn't always a right answer for that. And it's part of like the process of working this through, is kind of figuring out what data you include and how do you include it. So let me pause there. Any questions? Okay, I have weighed you all down into submission. So then let's see, what else do I have here? Okay, one other thing I gotta talk to you guys about. Okay, scaling your data. Again, another thing, I'm going to introduce a topic. We are going to spend more time on this later, but you just, again, something to be aware of. Oftentimes, it is going to be important for you to try and scale your data. And sometimes your machine learning model will not be impacted by the relative scale of the features, but sometimes it will. And so as a general rule, it's always a good idea when you're dealing with numeric features to scale them. And what do I mean by the scale of your data? So imagine, for instance, that I have a data set that looks at, let's say I have a data set of employees. And so I'll collect things like their age, which will be a feature in, generally speaking, in double digits, right? I will look at years on the job, which will be a feature in single digits, maybe double digits, right? But those are generally on the same scale. And then maybe I'll collect their salary. Well, that's a feature that's in the tens, if not hundreds of thousands. So the scale between those features is dramatically different. And some models, that won't matter. Other models will be highly sensitive to the relative scales of those. And in fact, we'll look at that and say, you know what? The only feature that's of any value here is income, because all those other values are so minuscule, they just simply don't factor in. The only thing I'm going to focus in on is income. And that's clearly not necessarily what you want to do. You may want your model to treat all features equally. You may say, it doesn't really matter what the scale of the feature is. I want to treat all of these equally. And the way to do that is to just scale your data. And there are ways to do that. The way that we employ here is a standard scaler, but there are other options to do that. There's, I think, a normal, I mentioned a min-max, a normalizer, but standard scaler takes your data, takes the min-max value and puts that within the range of, so it shifts your data distribution. So it's now centered around 0 with a standard deviation of 1 and -1. So if you think about your data, it could be values in the millions or even billions. You've now shrunk it down such that it's centered around 0, 1, -1. And that is what I do here. And I'm going to get into what this specific thing is in a moment. But essentially, I have scaled my price. So if you recall here, my price was 16, 18, 410, whatever. After scaling it, I get these values here. So That's what I'm doing when I am scaling it. Okay, any questions on scaling? I know I'm throwing like so much information at you guys. It's kind of brutal, but like, you guys feeling okay with that one? Okay, oh, let me see here, hang on. Okay, oh, so there's a question. Oh, sorry, there's a question about null values, and was that addressed or is that still active? Oh, okay, cool. Okay, never mind. Okay, so again, here's just a way to scale that. I'm going to talk a little bit about this in a moment because we're kind of leading towards our pipelining thing in a moment, but just so you're aware, it's an easy way to do this. You import all these libraries already imported. There's this sort of column transformer thing, which is really what you'll use to make your pipeline. And then from your pre-processing, you could just do various standard scalars. You then, there's this really nice framework. I'm going to get into how it works, but essentially you just define your method. In this case, it's going to be a standard scalar. You apply it to price, and then you run the fit transform, which essentially applies this sort of pre-processing step. So I'll walk through each of those in a moment, but that's essentially what you would do to do this. And again, we'll look at how that works specifically in the context of pipelining in a moment. Let's kind of look at this again with sort of a broader thing. So preparing my final data set. So I'm going to do two things. I'm going to one-hot encode my two variables, so my two features. So neighborhood and type, I'm going to turn them into one-hot encoded features. And then I'm going to scale my price. And you can see we have this nice kind of pre-processed thing, which is essentially the way I would define that is like I am making, this is my ingredient, basically. This is my cookbook. So I'm telling my pipeline, when you see the price feature, apply a standard scalar to it. When you see neighborhood and type, you one-hot encode those, and then you output that as a NumPy array. And then, so I've defined my pre-process method. I then do the fit transform to my data. It runs that, and then it outputs this beautiful NumPy array that I can then just feed directly into my machine learning model.
Sorry, do you mind explaining the very last step, the fit transform?
Great question. Okay, so the way of thinking about this is this pre-process step, again, that is your instruction manual. That's your cookbook. That's your ingredient list. It basically, you define kind of what you want done to each thing. The fit transform method is actually doing it. It's saying sort of apply this recipe to this data. So that's kind of your working function for that. It's saying fit this transformation to this data and then output the array.
Thanks.
Yeah, absolutely. And at a very, very high level, this is precisely what you're going to be doing for your pipeline. So if you kind of keep this framework in mind, that is exactly what you're going to do for your pipeline. Okay, so let us go back to this for a moment. So if you're going through your project one workbook, let me kind of tab over to it. Okay, it would be helpful if Zoom would actually let me do that. Okay, here we go. So everything here is looking fine, looking fine. I'm going through this. I'm like, okay, I got this. I got this. This is fine. Augmenting my features looks great. This is great. This is great. Okay. You know, looking at my incomplete thing. So, oh, just kind of zooming back to this, dealing with incomplete data. So you can see here, here was one example, dropping the rows that have the null values. So you can drop the incomplete feature. These are things we talked about. You can apply, you know, one of the methods, filling it, right? These are all kind of imputation methods. So all that's looking good. We're good. Everything's good. We're dropping our features. And then we get to this just block of text. And it's like, what happened here? So this is the pipeline. And this is kind of a mess. So I'm going to kind of walk you through exactly what we're doing. And again, just bear in mind exactly this example that we walked through here, because we're just doing a slightly fancier, slightly more spiffed up version of exactly this. So let's work from the bottom. Let's peel this like an onion. Housing prepared. So that is going to be your output. That's going to be your NumPy array. And what you're going to do is you're going to take your full pipeline, which remember is your recipe. That's your instruction manual that you're going to define. And you're going to do the fit transform function on housing features. So that is your input. That's the data frame that you're going to input in. You're going to do your recipe. You're going to get your fully pipelined output. That's your goal. So remember when we talked about the whole reason we're doing this is we want to get this nice, beautiful kind of single method call that you can do so that whenever you're in a production environment, whenever you have data that comes in, you can just call this, this full pipeline fit transform on it, input your thing, you get your nice little output, you plug that directly in your model and you're good to go, right? It's a nice, beautiful thing. Okay, our recipe guide here, this full pipeline. So we use the column transformer because again, that defines what we're going to do. And then there are sort of two things we're doing here. We have our we define these are arbitrary, but we're going to say, okay, we're going to do two types of things. We're going to handle our numeric and our categorical a certain way. And these are arbitrary. You can define them however you want. And then for our numeric, this is the instructions we're going to run, our numeric pipeline, and we're going to do it on these features, our numeric features. For our categorical, we're going to just do one hot encoder, so no need to do any kind of fancy definitions for it, just one hot encoder, and do it for our categorical features. So that is what our pipeline is going to look like. Now we're going to fill in what those variables are. So categorical features, that one's easy. It's just ocean proximity. So we saw that before. Our numeric features are, in this case, it's a list of housing numeric. And housing numeric is something that Sajjad defined. Where did he define that? Where did he do that? Housing numeric. So he just took your housing features and then he just dropped ocean proximity. And we're calling it as a list because he wants the features. So essentially we want a list of the features for housing numeric. So now we've got our categorical features, we've got our numeric features. We already said we're just doing one hot encoder, so that's fine. The only other thing we need to do is this numeric pipeline. And for the numeric pipeline, there's a few things that we need to do. So here, the same kind of deal. Okay, so there's three things here. So for this, we're going to define an imputation strategy. So for our imputer, we're going to call the simple imputer method. Our strategy in this case will be median. So it says whenever we get a null value, we just simply put in a median thing. We're also going to augment our features. So, and we're going to do this augment features method here. And we're going to talk a little bit about that momentarily, but that's essentially what we're going to call that. And then finally, we're going to scale our data. So we're going to take all of our features and we're going to scale them. So that's our numeric pipeline. So again, looking at this here, full pipeline, we have our numeric pipeline, which we've just defined, and the features, which we've defined. And then we're going to one hot encode our categoricals, and we defined our categorical features there. So that's that. And we've already talked about standard scalar. We've already talked about simple imputer. The last thing we can do is this augment features. And this is probably the one thing that's a little bit tricky. I'm going to tell you right now that for your own pipeline, I don't know that we're going to ask you to, let me see here. Are we going to ask you to augment as part of that? So I'll say try to implement this, but if it's tricky, don't worry about this because this gets a little bit tricky is what I will say. So part of the reason that this is tricky is because you will be inputting a pandas data frame. So one of these nice little things here, but you will be outputting a NumPy array. So if you remember last week, we talked about kind of the differences in functionality. And one of the challenges with that is you lose the ability to do easy column references. Here, it was very nice and simple. You could just define price and say, apply this to that. Once it's in a NumPy array, you don't have an ability to reference columns by their name. you have to do them by their relative index value. And so this whole thing here is really just about, so we've already done these here. So we already up here, where did he do the augmentation stuff? So here, we already augmented these using pandas. Here, he's augmenting those same features, but he's doing it using NumPy references. And he does that by defining the relative index IDs. So he defines those variables here, and then he inserts them here. And again, the coding there is a little bit trickier. I'm debating whether or not I should publish some simpler code for you to use, because it could be a little simpler than this. But what I would say is that's probably the trickiest thing in this entire project to implement. So if you're struggling with that, I'll probably either publish, for sure during office hours, I'll walk through it. But if you're struggling with that, maybe I'll publish some sample code that can kind of help you just simplify this. Because this is probably the trickiest thing in the entire thing, is just defining that specific feature for that. But other than that, that's pretty much it for your pipeline. So yeah, so again, it's like a lot, but it's fundamentally the same concept that we're working here, where you're defining your your instruction manual, you're applying it for the data. Within the instruction manual, you define a set of class, a set of instructions, and then what data you're applying that to. And so it's the exact same thing here. So the NumPy array you're going to output, this is your instruction manual, this is your fit transform that you're doing it, this is what your input is. Your instruction manual is just you're defining a set of rules for your numeric and your categoricals. For your numeric, you're going to follow these rules, which we've defined up here, and you're going to apply it to these features, which we've applied here. For categorical, you're just going to choose these rules and you're going to apply that here, which again, we've applied here. And then probably the trickiest part of this whole thing is just developing a custom method for inputting, for augmenting your features, and using just a NumPy approach versus the pandas approach, which is much easier. So that's pipelining in a nutshell. Yeah, so that's what this whole monstrosity is. So we've already kind of talked about this, but again, and we'll talk about this a little more, but it's just the whole idea of, when you're looking at this data set here, when you're working with data science, a lot of it's experimental. You're going to see this with these projects. Like you'll work in these NumPy notebooks or in these Jupyter notebooks. You'll try different feature combinations. You'll try dropping different features. You'll try experimenting with different combinations. And Jupyter is really great for that in terms of like experimenting. But if you're hired as a data scientist, let's say as a real world example, let's say you're hired by Airbnb to solve the exact problem that you're doing, eventually you want to export your model into their production code. And the whole use case of the process flow is a new user registers their account. They fill in information about their Airbnb listing. That information should be sort of pipelined, plugged into your model. A prediction should be returned and then auto-populated onto the site, right? So that's kind of the workflow and how that works. Well, obviously, that's not going to happen on a Jupyter notebook. You clearly need just a nice, clean code for production. And that's really what the pipeline step is it's turning all of this experimentation, all of this kind of tweaking into this nice, easy, simple method that you can call, that whenever a user in production inputs some new data, you just plug it in, you get your pipeline. You would then take that data, plug it into the model that you've trained, get your output prediction. So I know that's a lot, and I'm sorry I threw that all at you, but let me pause there, see if there's any questions. Let me just pull up the chat.
We were just talking about how you're probably going to have a lot of people visiting you on Monday.
Yeah, oh, that's true. Should I move my office hours to Sunday?
I mean,
I could probably do that. Yeah, screw it. All right, I'll do office hours on Sunday. I'll send out a note about that. I agree. Monday night office hours is not going to be helpful. Okay, office hours are going to be Sunday night, 8 to 10. Good call.
Cool. Thanks.
Yeah. But let me see. Okay, are those three methods done? Yeah. So how young? Good question. So right now, so you have the question of, are those three methods done on all numeric columns? So right now, the way to think about this is it's not done to all numeric columns. It's done specifically to the columns that you've defined here. So in this case, the numeric features, which happen to be the list of features there. What you can end up doing, and the reason why this is so cool, is you can end up doing multiple numeric pipelines. You know, for instance, there's some where you may want to do the imputation strategy of median. There are some where you might say, just drop it if it doesn't exist. There are some where you might say, or use a different strategy. So the point is, you can theoretically do as many of these as you want, and without it necessarily being, without it. So in other words, it's purely arbitrary. And this whole numbering thing is just for you to keep track of it. So I could theoretically do, like, for each numeric feature, I can create my own pipelining step. I can do different ones. Some of these, like even for my categorical, some I may want to one-hot encode. Some I may just want to, use their existing, I may want to label encode. Some I may want to do some other kind of custom encoding, right? And all you're doing with this is you're saying, what features do you pass through, and how do you do them or not? There may be, for all you know, some features you don't want to pass through, or there may be some you want to pass through, but you don't want to actually do anything with them. So that's something you could do as well. But yeah, great question. And then let me see. I'm checking the chat on my phone, and I got booted on my phone. That's not great. Okay, so let me just pull up the chat then here so I can just see if there's any questions. Okay, so yeah, so in this case, list housing numeric. So again, up here, so what Sajjad had done over here, housing numeric, is essentially he had taken our initial features, our full data frame, and he had dropped our categorical. And so what he says is essentially, these are going to be the ones we're going to treat as numeric. And then here he just called a list because he wanted to generate a list of the column names associated with that. So what it's saying is essentially you do the numeric pipeline specifically only on those features. So Wei Yuan, I don't know if that's what you're asking, but yeah, that's the thought with that. Okay, cool. Yeah, my phone's not working, so I'll just have to look on the chat here and just hope it doesn't show up on the recording. All right, back to the slides we go. We're almost done, people. I swear to God, we are almost done. Okay, yeah, this is pretty much what we've already discussed here. But again, it's on the slides here. So I'm not gonna not waste any more time on that. Okay, time to split our data. So we kind of teased this, we kind of previewed this. Reality is, man, sometimes breakups just happen, and you're going to do that with your data set too. And when it happens, just you gotta just vibe it. So be in the moment, put on some Olivia Rodrigo, just feel the breakup. But yeah, training, testing, splitting your data. So remember, we talked about that. Where's my chat here? Okay. So, oh man, if you are not on the whole driver's license bit, you gotta do it. And then she put out a new track, Deja Vu, which is really good if you haven't heard it. Just throwing that out there. It's good, man. The teenage person in me just vibes it. It's my jam. Let's talk about it. There are multiple ways in which you can split your data into training and testing cohorts. And this is a whole other thing that we are going to talk about. This is a whole other thing. It's like, what? Like everything we touch on, I feel like that's my whole thing. It's like, oh, here, we'll come back to this. We'll come back. Yeah, so this is another thing we're going to come back to this. But we need to split your data into training, the thing that you actually sort of train your model on, and then that testing, that validation step. Does it work? Does it not work? This is probably the easiest way to do this. So it's train test split. It's an automatic randomizer way to just kind of split your data. And Generally, it's either an 80-20 or a 70-30 thing. But so essentially, the inputs for this are you get your X training, which is your sort of your features for your training set, and your labels for your training set. So X and Y are features and labels, and then your features for your testing set and your features for your the labels for your testing set. And then you do this train test split. You get your inputs, which is your data frame. You get your Y, which is your labels. And then you just define, in this case, it's going to be an 80-20 split. Let me think, what else do I need to tell you about this? I feel like I need to tell you more. Do I tell you anything? Oh, okay. Here's one thing I'm going to talk about here. This random state thing. So this is kind of an important thing when you're running your model, and it's a good practice to get. So I know Professor talked a little bit about difference between like arbitrary, random, and whatnot. This is a random seed. Does anybody know what a random seed is?
For random number generation.
Okay, good. But what is seeding that do? Why is that important?
Gives your pseudo random number generator like a starting point, so that it can determine like what the sequence of random numbers will be.
Good. Okay. So Godfrey, I think you nailed it there. So here's the idea. This train test split will do it at random, but it uses sort of a pre-programmed algorithm to generate that random data set. If you do not seed it, it will start at a different origin point every time. And the result being that you will get a slightly different data set. Your training set and your testing set will end up being different every time you run that thing. And there are actually sometimes when that's a good thing to do, but the really bad thing about that is it kills consistency. So if you run your model and on a certain data set, and then you rerun your model on a completely different now data set, you will likely get very different results. And so if you want to make sure that you're getting consistent results, you want to make sure that if, for instance, you do this notebook and then you send it to your friend and they do this notebook, they will get the exact same outputs. You want to seed your randomized function. And so that's exactly what that random state is. You're defining sort of that seed that it'll essentially start its randomized algorithm around. So you're going to do that splitting step. Then the last thing we need to do here, we're almost done. Well, second to last thing is we've got to select our model, we've got to train it, and we've got to look at our outputs. So do I have good slides for that here? Yeah, okay, I'll go through that in a moment. Oh, one easy thing to note here for your one kind of sanity check that you can do for this is you can output your data frame after you've done the split just to kind of do a sanity check here. And so in this case, I'm going to look at, so I printed out my my training features, my training labels, my testing features, and my testing labels. And here's the sanity check you want to look at. So the first thing I want to look at is I want to say, okay, well, do my testing and training features, do we have the same dimensionality? And in this case, the answer is yes. Both of these have 10 features. So that's good. The second thing we want to see is there a direct match between feature rows and associated labels? In this case, yes, there is. So for each row in my data set, I have an associated label with it. So that's just kind of like an easy sanity check that you can do just to make sure that that worked properly. So the final step for us is we're going to import our model. And so we're going to use scikit-learn. In this case, we're going to import a linear regression. In this case, I'm going to define a specific instance of it. So in this case, linreg is going to be my actual model. And I'm going to say it's an instance of linear regression. I'm going to then use that fit. And fit is very similar to fit transform, but it's the idea that I take linear regression and I'm going to train it on my training data, my training features, and my training labels. So that's in this case what training and target is. And so that step is then going to be, it's going to do a fit thing. So the final thing I'm going to do here is, okay, what does he do? Okay, Then he's going to take his testing data. So this is my testing features, and my label is my target test. And so here's what I'm going to actually do with this. So now that I have trained my linear regression model, I'm going to then take that trained model and I'm going to call the predict function, and I'm going to use that for on my data. So in this case, I'm going to generate a series of predictions. So in this case, you're going to see here prediction, 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 and he outputs the actual labels. So this is what was predicted. This is the actual label. This is what was predicted, the actual label, predicted actual label. As you can see, it doesn't look that great, but it is what it is. As the final thing that we do, we then import our metrics. So remember, we said we were using mean squared error. So in this case, we define our set prediction. So in this case, we now, instead of doing it for just a subset, we call our model and we run the prediction against our entire testing framework. And then for that, to get our actual output, we just do mean squared error against our actual label versus our predicted labels, right? So if you go back here, mean squared error is, so remember, we have our, I think it's actual minus predicted. So that's essentially what we're generating here. This is our actual label. This is our predicted label. And then that will give us our mean squared error. In this case, he also has us do the root mean square. That's another metric you can do. And here he just takes the square root of MSE and he outputs that. And that is your root mean squared error. But you are just asked to generate MSE for yours thing. Yeah, you're just asked to do MSE. So that in a nutshell is what you are asked to do, I believe, right? Let's see, is that it? Oh, no, I did not actually play it, sorry. Okay. Oh yeah, this is a funny slide. Okay, so we talked about this. I'm gonna not dwell on this a little bit easier, but this is something we're gonna spend more time on. Results, how do we interpret the results we get? What is a good result? What is a bad result? Let's just note that there isn't an absolute, this is good, this is bad. It's going to vary very heavily depending on your model, depending on your targets, depending on your tolerance for errors. Part of your job as a data scientist and understanding a problem and scoping it is understanding and interpreting your results and saying what is and what isn't an acceptable result. So I did just kind of want to note that. So, whew, that's a lot. Okay, I threw a lot at you guys. I'm sorry. Man. All right. Any questions now that I have beat you all into submission with that? Okay, so I can be reactive. Should I have some later? Okay. Cool. I'm gonna stop the recording then.